Hello, today we will be sharing our presentation which outlines how to build a successful startup in Los Angeles. Next slide. Taking a look at today's agenda, we'll start off by providing some background on the study, which will provide us some context as to why this study was chosen and its potential impact on new businesses looking to enter the LA market, as well as lay out the business problem and give a brief description of the data we're working with. Then we will cover the data pre-processing steps that we executed in order to clean and partition the data to prepare it for analysis. Next, we will walk through the various models we've prepared and examined to ensure suitable fit and accuracy, such as k-nearest neighbor, naive Bayes, neural network, support vector machine, classification tree, XGBoost, random forest, and logistic regression. Following that, we will be comparing the performance of the aforementioned models in order to select the model that provides optimal accuracy. Lastly, we will be wrapping up with some key takeaways and study limitations. Next slide. Now, a little about the background of the study. Our overall goal is to be able to provide companies with insights as to how to launch a successful business in Los Angeles. The purpose of the study is to identify which attributes are most critical to the success of a business. As noted in a May 2019 article from Business News Daily, also cited in our appendix here, California is home to more than 4 million small businesses and a large variety of complex regulations that govern those businesses' actions, making California a highly competitive state to launch a business. Our expectation at the end of the study is to have new businesses be able to emulate the decisions and attributes of past successful businesses in order to create a business that exhibits initial success and ideally long-term growth. Next slide. So how are we going to accomplish this? We will be taking 3 steps to meet our goal of being able to identify which business attributes can lead to success. First, we will need to obtain some attributes of businesses that we already know are successful. Next, we would need to ingest that data into various data models that we feel would appropriately predict our desired outcome. Lastly, we will compare the error rates of each of these models and from that decide which will produce the most accurate results. These steps will lead us to accomplishing our goal, which is to identify business attributes that result in success and ultimately allow investors to make a final business decision. This will be able to tell us which of these attributes they should focus on to obtain and ensure their future success. Not only will this study help mitigate financial risk, but it will help mitigate the career risk and psychological risk placed on investors that come with a failed business, as discussed in the European Journal of Management and Business Economics, also cited in the appendix for further referencing. With that, I will pass it over to my group member, Jason, to introduce us to the type of data we will be working with.
Thank you, Tania. Now I will be talking about the data description. As we mentioned in the last slide, the goal is to find which dependent variables affect the outcome variable most. Therefore, the team will try several methods such as the KNN, the neural network, and etc. to create the best model for the variables. This will not only help the companies to improve their rank, but also give the investors ideas about how to invest. This is the original dataset. And our team divided the variables into groups to have a better sight of how to clean and transform the variables. We divided the variables into 5 groups. The first group is the outcome variable, which is the rank of the company. Second is the company's information, which includes the name of the company, what industry is this company in, what does this company do, when is this company founded, and where is this company. Next, the founding groups includes the last founding date, the founding status, IPO status, last founding amount, last founding type, number of founding rounds, and the total founding amounts. Then is the assets group, the company's acquisition status, estimate revenue, the number of patents and trademarks will all be included in this group. The last but not least, the relevant personnel. This group contains the number of employees, founders, investors, and the lead investors. Now I have done introducing our original dataset. Let's move on to the next topic, and Tom will talk about the descriptive analysis. Next slide.
Thank you, Jason. So the data set for this project has 2,000 records and 17 variables. And below are the plots and numbers that the team found that are interesting. So variable Y0 will present the company with the CB ranking below 10,000, and 1 presents the company with CB ranking above 10,000. The first is the location. We found that Los Angeles, Santa Monica, and Irvine are the top locations for startup companies. Next slide. And for total funding amount for Y variable equal 1, the most probable funding amount is from 10 million to 50 million, while for Y variable equals 0, the amount is from 1 million to 10 million. Next, I will invite Yida to talk about data cleaning.
Thank you, Tom. Now let's talk about data cleaning. The first task we completed was irrelevant variable deletion. When we are first looking at the original data set, we found that 8 columns can be removed directly. As you can see in the tables, first we have organization and person name URL, which simply provides organizational or personal links in Crunchbase and does not contain any statistical information. So we deleted that. For the same reason, description, which are brief descriptions of the 2,000 companies, was removed as well. For IPO date, because a large proportion of the companies in the dataset are private companies, so IPO dates does not make any sense to them, so we remove that. A number of events, 71% of the observations of the variable are not available. To avoid creating bias, this one was deleted as well. Also, the original dataset contains 2 similar columns describing industries. So here we only keep industry group instead of industries, which looks more comprehensive. And founded date, precision, for the same reason, no statistical information either, so we deleted that. For currencies, all of them are all in US dollars, so there's no need to keep them as variables. Next slide, please. And then we're talking about variable transformation. And this is also a very essential part in this project. First, we have transformations between categorical variables and numerical variables. For example, because some continuous values have wide ranges like total funding amount here, we set ranges manually with reasonable incremental first, and then make them to ratio variables. And we also have variables converted between nominal and continuous. For example, like locations here. The original variable listed tons of cities, and we wanted to make it more suitable for statistical analyses. We transform it to latitude and latitude. And dates are also very interesting variables, but not very appropriate to be fit in models. So we converted those dates to days as continuous values. And next, we created a lot of dummy variables. For nominal ones, just convert them to several factors or labels. And like IPO status, we now have IPO status delisted, IPO status private, and IPO status public. And for continuous variables, we set ranges manually, like mentioned above, and make them into labels. Next slide, please. And then we are talking about missing value treatment. First, replace NS with mean or median value. And this method is typically applied to numerical variables. One variable contains large integers, the range is wide, and the missing values are not too many. And second, we replace NAs with 0. We use this approach to handle NAs if a certain variable is binary and there are not too many NAs. And then we also converted NAs as a factor. And this is also the most common method that we implemented in this project. As most of the categorical variables in the dataset consist of a large number of NAs, we think it is more objective to transfer them into a factor to avoid creating bias from replacing them with other values. And last one will be KNN-based imputation. For categorical variables, when number of NAs is very limited, we think it is not worth transferring them into a factor. So we use the K closest neighbors to the observation with NAs and then imputing them based on the non-missing values in the neighbors. Next slide. After doing the 3 steps above, we can now have a summary of our data. And now we still have 2,000 observations, in other words, 2,000 companies. And the original data set contains 1 dependent variable, which is a CB rank, and only 20 independent variables. And the clean data now includes 1 dependent variable, which now is a binary variable. The rank below 10,000 as 1, and the rank above 10,000 as 0. And we also have 144 independent variables. The figure on the screen lists all those independent variables for your reference. Next slide.
Okay, so after the data was cleaned, we partitioned the data into 2 parts, training data and also the validation data. We partitioned it randomly, and we partitioned the 70% of data into the training data, which contained 1,400 rows. And also for the testing data, we have the 600 rows. So the distribution is looked like this. Okay, next I'm gonna introduce to the modeling.
Okay, so KNN has 2 functions, classification and prediction. In this project, classification is the only function that is used to classify under what conditions the company will be in what rank. So the team uses 75% of the data as a training data and the rest of it as testing data. By using 0.5 cutoff, the best K is 7, and it provides the lowest error rate, which is 0.21. And the highest specificity of 0.895. When the team tried to lower the cutoff rate, the result is that from 0.4 to 0.1 cutoff, they all have the same best K equals to 1. Moreover, the error rate for cutoff from 0.4 to 0.1 is 0.26, and the specificity is 0.825. Therefore, the default cutoff rate of 0.5 has the best performance. Next, I will transfer to Summer to talk about the next content of naive Bayes.
We also applied the naive Bayes to our data set as a benchmark in this case, set all outcome Y as 0 in the result. As the figure shows, the count of ones indicated the benchmark provides 23.8% error rate. Next, please. Other than that, we conducted a neural network analysis as well. We implemented backpropagation neural network analysis, come up with 2 methods, single layer and multi-layer. The result has been displayed in the figure. As we can see, both methods provided lowest error rate and highest specificity at the cutoff equals 0.5. Also, as the cutoff gets lower, the error at the sensitivity gets higher and the specificity gets lower. Next, please. This figure is our single layer plot. In this case, we found out the drawback of neural network applied in our data set in this business situation, which is actually a black box, and it's hard to tell which variables and to what degree they can be significant or influential to the outcomes. And then I will pass to Jonathan.
Okay, so next we also applied this modeling to the support vector machine. So basically the support vector machines use all the variables to create a one hyperplane to classify the binary outcome. And the data point that's close to the hyperplane is called a support vector. So the pro of the support vector machine is that it's good for large data sets with large variables like our data set, but the con is like it's hard to predict. It's also the black box. It's hard to predict how the modeling was performance in the between. And for the model, it get high specificity when the cutoff was 0.5, and it get a lower error rate when the cutoff was 0.4. Okay, next.
Now let's look at the classification tree and XGBoost. Since both of them are tree-related algorithms, we can use original numerical variables and do not need to standardize them. Therefore, we bring the total funding amount and the last funding amount back into our data set for these two methods. The result of the lowest misclassification error for classification tree is 0.215 when the cutoff value equals 0.5. The highest sensitivity is 0.8282 when cutoff equals 0.2, and the highest specificity is 0.5745 when cutoff is from 0.3 to 0.5. Next page, please. And here is the minimum error tree graph generated by the classification tree model. Next page. Now we're talking about XGBoost. XGBoost, also named as extra gradient boosting method, with benefits of cross-validation and feature selection. Another good thing about it is it can process missing values by itself, so we don't need to worry about that. For XGBoost, the lowest validation error is 0.158 when cutoff is equal to 0.5. The highest sensitivity is 0.9568 when cutoff equal to 0.1, and the highest specificity is 0.7222 when cutoff equal to 0.5. XGBoost can generate a figure of the importance of all features we have used. The top 10 most important features are listed here. From that, we can clearly see that the total funding amount, days after last funding, and days funded are the most important features in our model. So we can assume that the company's funding condition and its lifetime may mostly decide our decision. Yes, next, let's introduce Han to talk about random forest and logistic regression.
Thanks. So random forest is another tree-based algorithm that helps provide high accuracy in single decision trees. Let's first look at the table. We have a highest specificity of 0.96 when cutoff equals to 0.5. When cutoff is 0.4, we can get the lowest misclassification error rate, which is 0.15. And when cutoff is 0.1, the result gives us the highest sensitivity, which is 0.89. Next, please. Since random forest is just like a black box, we cannot see which variables exactly contributed to the lowest error rate. We can only use mean decrease accuracy and mean decrease Gini to find what variables are relatively important. In this case, day after last founding, founding status C, last founding amount, days founded, latitude generated, longitude generated, category 20, number of founding rounds are more important than others. Next, please. Logistic regression is the last supervised learning method we implemented. As you can see, by using forward variable selection, we can get a lowest error rate of 0.155 when cutoff equals to 0.4. Also, the highest specificity, 0.926, is provided by a cutoff value of 0.5. The highest sensitivity, 0.909, is provided by cutoff equals to 0.1. Similarly, as for a stepwise variable selection, you can get a lowest error rate of 0.157 when cutoff equals to 0.4. Highest specificity 0.93 when cutoff equals to 0.5. And the highest sensitivity 0.895 when cutoff equals to 0.4. Next, please. The output generated from R is showing on the screen for both forward and stepwise method. 35 variables are significant at the significance level alpha equals to 0.05. The most the most significant ones are listed for your reference. Next, please. Moving forward to the model performance comparison, the table summarizes all the misclassification error rates, specificity, and sensitivity. Here we only focus on the lowest misclassification error rate under different cutoff values. When cutoff equals to 0.5 and 0.4, random forests give us two lowest error rate, 0.155 and 0.1517, respectively. When cutoff between 0.1 and 0.3, logistic regression has best performance. The error rate are 0.26, 0.193, and 0.157 respectively. And I'll now pass to Jonathan for the takeaway.
Okay, so for the conclusion, takeaway, we take the variables that were important based on the best performance model, which is random forest. So the conclusion can take into divided into three parts, which will help three types of people. So the investor, the graduate student, and also the entrepreneur. For the investor, we will suggest that they will focus on the recent funding activities. And also for the graduate student like us, we will suggest that they will looking for the company that's recently received the funding, and also the startups company in the seed round. If they're looking for a funded company, they should looking for the company that's funded for a long time. And also for the entrepreneur, they should carefully selecting the location. For example, in the data description part, we're suggesting like the Los Angeles downtown and also Santa Monica Beach and also urban is good place to start a company. Next, we're going to pass to Yida.
Thank you, Jonathan. And we do have some limitations during this project. The first will be definition of success. We assume that a company with a ranking below 10,000 is more successful. However, these rankings are generated from a third-party Crunchbase, which may have some bias or subjective views. And also, how do people measure success? Different people may have different opinions about that. In terms of a macro perspective, the data or analysis based on those data only evaluate the performance of companies in general and maybe not applicable for certain company. And our information in hand is still limited. Although we have 144 independent variables already, there will be tons of other factors that will influence the performance of a single company. And algorithms we have learned are still not too much. We would like to learn more models to do a more comprehensive project in the future. So this is our presentation. I hope you enjoy it. Thank you for watching.